All right, hey folks. Today's alternating series, day 4. One of my favorite tests actually because it is so simple. So let's get started. All right, so what is an alternating series? So let's first take a look at this example. Here I have my first term 1/2, then 1/3, then 1/4, then 1/5, then 1/6, then 1/7. But you'll notice that the sign is alternating: positive, negative, positive, negative, positive, negative. All right, or the first term minus the second term plus the third term minus the fourth term. The first term could be negative as well. It doesn't matter as long as they're alternating each time. So the conditions for the alternating series test is that the terms must be decreasing and never equal, right? So always decreasing. So you can use the derivative to check for decreasing un, right? So just take f prime of n and show that it's less than 0 for all values within the domain of the series itself. Okay, so and the second thing is if the limit of this sequence, right, now this is the sequence, the non-alternating portion of it, right, so just un, not the alternator, which we'll talk about in a minute. Okay, if it equals 0, then the series converges. So all it has to do is be decreasing, and the limit of the sequence has to go to 0, and then we know that it converges. So let's look at a visual of this, right? So we said that the first term was 1/2. Okay, so we start at 0, we add 1/2. Now we're over here. So that's our sum of our first term. Then we subtract 1/3. That brings us back over here. That's the sum of our first two terms. Then we add 1/4. There's S3. Then we subtract 1/5. Then we add 1/6. Then we subtract 1/7. What are we doing? We're basically oscillating back and forth until we get to this value right here, which is our infinite sum. All right, so that's what an alternating series will be doing visually. Okay, so what would an alternating series potentially look like? Well, let's see here. Let's say that we're going from n equals 1 to infinity of -1 to the n over n factorial. Let's write out a couple of terms. Okay, so our first term would be -1 to the first over 1 factorial. Our second term would be -1 to the second over 2 factorial. Our third term would be -1 to the third over 3 factorial, and so on and so forth. So any odd degree I'd have a negative coefficient. Right here I'd have 1 over 2. Here I'd have -1 over 6, and so on and so forth. So this right here is a typical alternator. That's what we'd call an alternator. But what we'd call u sub n in this case, of course we want the limit as n goes to infinity to equal 0. But u sub n in this case is going to be everything except the alternator. So we would have 1 over n factorial. If that went to 0, we're in business, right? So the two things, let's review. The two things that need to happen in order to have a convergent alternating series is it must be decreasing. Okay, so what that means is that u of n plus 1 needs to be greater than u of n, and the limit as n goes to infinity of u of n has to equal 0. So it's an easy 2 steps. Let's do a little bit more with it. Okay, so to approximate the sum, the infinite sum s, by the partial sum s of n, this I'm gonna go through. I'm gonna try to help you understand the language going on here, but then I'll give you a very, very nice understanding of what this means in layman's terms. So, okay, we have an error of the first n terms. Because this is an alternating series, we have the absolute value of the difference between the actual sum and our partial sum of n terms. right? So that should be pretty familiar from what we've done in the past couple of days. What this right here means is that the error R sub n is always less than or equal to whatever the next term is, its absolute value. Okay, so if I wanted the error on our previous example, if I wanted the error of the first 3 terms, right, of the series n equals 1 to infinity of this alternating series here, right? I think we said it was 1 minus 1/2 plus 1/6. Well, here what I have is, I have s sub 3. It'd be whatever that comes out to be. Let's see what that would be. The sum of the first 3 terms here would be, let's see here, 6/6 minus 3/6 plus 1/6. So it looks like that would be 2/3. How far off? How far off would that be from the actual, right? Well, how far off would that be? Would be whatever this next term is, whatever the absolute value of this next term would be. Well, we know it would be a negative, right? It would be negative, what would that be, 1 to the 4th, so it doesn't really matter. Oh, I'm sorry, it'd be, that's 1, that's 2, that's 3. Oh, I'm sorry, whoops, I got this backwards. This was negative, this was positive, this was negative, this one will be positive. 1 to the 4th over 4 factorial. Okay, so that flips everything here. So that'd make that negative 2/3. When in actuality, this is how far off it would be from the actual. So R3, our error, will be less than or equal to 1 over 24. Okay, you just take the next term, its absolute value will give you how far off from the actual that would be. Alright, so let's show here that the alternating square harmonic, okay, square harmonic series converges. So we got to do those 2 things, right? Let's look at what the square harmonic would be. N equals 1 to infinity of 1 over n squared. Right, this is the square harmonic. Recall the harmonic. This is the harmonic here. This is the square harmonic over here. Okay, so let's prove that this thing is convergent. First thing we got to do is show it's decreasing. Show it's decreasing. All right, so if I took f of n, which is n to the negative 2, and its derivative, well, its derivative would be negative 1 over n. That's clearly going to be less than 0 for all values of n greater than or equal to 1. Okay, so it's decreasing. Let's find the limit as n goes to infinity. Ooh, and I need an alternator on this too. I forgot. Okay, forgot the alternator. Okay. I need to take the limit of u of n. Well, u of n would just be 1 over n squared. And the limit of that clearly is 0. Therefore, this would be convergent by the alternating series test. That's all you have to do, you guys. Sometimes it's a little bit more complicated, depending on the series that's given. But in this case, boy, just free chicken. Okay, so what number of terms will make this have an error less than 10 to the negative 6th? So what is 10 to the negative 6th? That'd be 0.0000, hold on now, 10 to the negative 6th, 0.1, let's see. Okay, let's just go with that. My brain isn't working right now. Okay, so I want an error less than that. Well, that means that I want a term, the next term, to equal that. Okay, so let's think about that for a second. So that means I want to know what number would give me a value of 0.000001 or less. So I guess I could do that. Okay, so let's write this thing as a fraction. That would be 1 over 100,000. Alright, now I need to be corrected here. This is only going to be 4 zeros, which would be 1 over 100,000. So 1 over k squared. Let's find out where that would be less than that. Therefore, that would mean this would be true. Right, when I change that and flip and make the reciprocal, that means I want k squared to be greater than or equal to 100,000. Alright, so therefore k would have to be greater than or equal to 316.227. That means I'm going to have to go out, in order to get that kind of error or less, I'm going to have to go out at least 317 terms. That's pretty far out, right? But that will ensure that the error is less than 10 to the negative 6, which is 0.00001. Alright, here is the alternating series test in proof form. Again, you want, we used u of n, but we want u of n plus 1 to be less than or equal to u of n, right? Just meaning that's decreasing. And then we just got to prove that u of n as n goes to infinity is 0. It's really a quick two-step process. You can look at this slide on your own. Okay, again here a little bit more with seeing how the when you start, your first term will be an odd partial sum, and then you get these even partial sums on the left side of the actual. So odds are to the right, evens are to the left, and then you start to work your way back in toward the actual sum, as you'll see down here. Okay, the alternating series estimation theorem, basically just telling us that the error is going to be less than or equal to the next term, the absolute value of the next term. Okay, here's a really good one. This is showing that, or finding the error correct to 3 decimal places. So let's walk through this one together. The alternating series right here, as you can see, here's your alternator. Now the power can be set at whatever the textbook or I decide to give you, which is just going to change whether or not the first term is positive or negative. That's all that's going to do. Over n factorial. So b of n, or our u of n, which we've talked about before, is 1 over n factorial. Now we do have to prove, technically, that this limit goes to 0. However, it's pretty clear, and infinity factorial is going to be a very large number, so 1 over that would be 0. But we use this idea that n plus 1 factorial would be less than 1 over n factorial. So our next term would be less than our previous term. So step 1 is a check there. Also, we know that 1 over n factorial is less than 1 over n. And since the squeeze theorem would allow us right here to know that this is the harmonic series, therefore the limit of 1 over n as n goes to infinity is 0. Therefore, by the squeeze theorem, the limit would have to go to 0. And therefore, the series converges. Now what we do is we'd find, we've got our infinite sum here. If we went out, let's say to the seventh term, it's 1 over 5,040. Well, 5,040 is less than 0.0005, which is 3 decimal places. Therefore, what we want to do is we want to just take the sum of the first 6 terms. That ensures us that a 7th term has a value less than what we're looking for. So therefore, our partial sum to 6 terms is this. All right, so now what we can do is use this estimation theorem, which just says that the whole sum to infinity minus the partial sum to 6 terms is going to be less than or equal to the 7th term. So we set up this inequality. Right? So when we take away the absolute values, that allows us to make this this conjoined inequality, or this compound inequality that has 2 sides to it. So if I took the actual sum minus the 6th partial sum, right? Maybe the 6th partial sum is bigger than that. Well, it'd come out to be negative, right? Or maybe the 6th partial sum, as we know, would be less than that. Then it would be positive, right? So the error could be on either end of this. So I add the 6th partial sum to both sides, and that gives me an estimation of what my actual sum would be. Now we know that it would be within this value on either side, right? So it's pretty dang close. It's within 3 decimal places of the actual sum. So that's what your estimation theorem will do for you. It'll allow you to set up an inequality and find a pretty dang close estimation of what your infinite sum would be. All right, so we're on to the homework. Double lightsabers again. Let's do maybe one from this page. Okay, let's look at B. All right, here's my alternator, -1 to the n. The first thing I want to show is that it's decreasing. So let's show it's decreasing, hopefully. If we can't, then it would be divergent, but if we can, it's got a shot. Okay, so b sub n would equal sine of pi over n. Okay, so let's see here. Let's turn this into a function. Pretty simple transition. And let's take its derivative. So the derivative of said thing would be cosine of pi over n times the derivative of the inside. Now this is where you might get sniped a little bit, but that would be negative pi over n squared. So the derivative is negative pi over n squared times the cosine of pi over n. Because of this negative right here, we know that f prime of n will be less than 0 and therefore decreasing. Okay, so part 1, decreasing, check. Part 2, limit as n goes to infinity of b sub n, or u of n, whatever you want to call it. Right? Well, if n goes to infinity, that's going to go to the sine of 0, and the sine of 0 is 0. Therefore, the limit as n goes to infinity of sine of pi over n would be 0, and thus this series, alternating series, will converges by the alternating series test. Oh, here's a really good one on the next page, part D. Where in the heck is my alternator? Well, here's your alternator. What? Okay, let's think about that for a moment. That would be sine of pi over 2 over 1 factorial. The next term would be sine of 2 pi over 2, which is sine of pi over 2 factorial. The next term is sine of 3 pi over 2 over 3 factorial. Now, for a moment, you're saying, well, the sine of pi is 0, and you're absolutely right. So this term will cancel, and it'll be gone. What is the sine of pi over 2? Well, it's 1. So your first term is 1, then you get a 0, then you get a -1, then you're going to get a 0, then you're going to get a positive 1, of course, over whatever your factorial is in that case. This would be over 6, this would be over 1, okay, etc. So you might be wondering, well, is that possible, right? Yeah, it is. You could use a sine or a cosine to be an alternator. Okay, and so then you just have to take, I wouldn't do the derivative here to show it's decreasing. What I would do is just look at it spatially. So b sub n is 1 over n factorial. So I would look to show that b sub n plus 1, just by inspection, is less than b sub n. So b sub n plus 1 would be 1 over n plus 1 factorial, which is clearly less than 1 over n factorial. So you could right there just say decreasing, good. And then in 2, kind of like we did in the notes earlier, the limit as n goes to infinity of 1 over n factorial. We used the squeeze theorem to show that that equaled 0. So therefore we could say that this series, I'm not going to write it all the way out, but this series that we have above will be convergent by the alternating series test. So you're going to run into maybe a situation or two where it's not convergent, right? It would just have to fail at one of these two, right? Either the first part or the second part. So it's actually a lot harder to see here in the first part whether or not it's decreasing sometimes, because the series can be a little bit mucky, and you can get kind of caught up in the understanding of, you know, fractions and stuff like that, and which one is smaller, which one is larger, right? So be careful with that. But I think that'll be it for today. So that is alternating series test, and of course the estimation of the error. So, alrighty, have a good one. We'll see you next time.